page 123, we were asked to read that for homework last night. We can see some examples of what Lewis diagrams look like there for chlorine, oxygen and ammonia. So Cl2, O2 and NH3. What Lewis dot diagrams focus on are just the valence electrons, so just the electrons that could be involved in bonding, and they are looking at what the bonding looks like between the atoms. So for example, if I have the oxygen one and just draw it the way that it's shown in your book, it looks something like this. We need to be able to name the parts that we've got here. Anytime you see a pair of electrons between two atoms, this is a chemical bond. In this case, it's pure covalent because they're the same atom, so the electronegativity difference would be 0. So here we've got the bond, and in this particular example, because there's 4 electrons, it's called a double bond. If there were 6 electrons, it would be a triple bond. Okay? So in this particular case, it's a double bond, and we will know from our electronegativity stuff from yesterday that it's a pure covalent double bond. The electrons around the outside, what we call lone pairs of electrons. You notice that they are arranged in pairs. This is important. Okay, this is sort of how they're arranged in your Lewis dot diagrams. So they're called a lone pair. All of these regions where electrons lie around an atom, in a molecule or in a compound, all of these are what we call regions of electron density. So there's a phrase you can use for all of these. This will become really important in about a week's time when we look at the shapes of molecules. So remember our homework for that, as it were, is to bring some lollies we can stick toothpicks in so we can start creating the shapes. So these are called regions of electron density. Because all electrons have got negative charge, these regions repel each other equally. Okay, so they repel each other equally. So in reality, these would be out here and these would be out here, being repelled at 120 degrees away. Lewis dot diagram doesn't show us that. We'll show you the sort of diagram to do for those in about a week's time. But our focus for this week is to get good at these and to know some of the exceptions to a rule called the Octet Rule. So how do we do this? Well, the first thing I'm going to actually talk about are the exceptions, or how to try to do this. Generally speaking, when you are showing these, we're trying to get 8 electrons around every atom, because that would be a complete energy level, or complete shell. And if we look, these are shared. That oxygen has got 8, and because they're shared, this one also has 8. So those 4 electrons in the double bond are shared by each of them. This, therefore, must be a covalent bond, not an ionic bond, and that's why this is stable. However, this little thing called the Octet Rule, sorry, I'm just going to label that. This little rule has got some exceptions. And the reason I did electronegativity first is because that's one of our first big exceptions. If it is an ionic compound, then it doesn't have to obey the Octet Rule. Only the non-metal has to. So, here are our exceptions. And I'll quickly say why for each of them. Ionic compounds do not obey the Octet Rule. Okay, so I'll give you an example. So for example, magnesium chloride would look like this. And you'll see the magnesium effectively has only 4 electrons around it. In fact, it has none. Because it's ionic, this is actually a 2+ ion, and these are -1 ions. Sorry, it's a really bad way to put it. So that's why they don't have to obey the Octet Rule. The cation is actually trying to empty an energy level. So when you do a Lewis dot diagram for anything ionic, it doesn't obey the Octet Rule. There are also a few elements that don't, and I'll quickly talk about the reasons for those. One of them is hydrogen. And the reason for hydrogen, even though most bonding with hydrogen is covalent, The reason for hydrogen not obeying it is because for it to have a full energy level, or first shell, it only needs to have 2 electrons. So it only needs to have 2 electrons to be stable. Another one that's really common that you'll find often this year is used to check your understanding of exceptions to the rule is boron. And boron, for some reason, is stable when it's got 6 electrons around it. And this has got something to the fact that it's kind of an ionic bond, kind of a covalent bond. So remember that continuum from yesterday? That's what makes things a bit awkward. So it acts more like an ionic bond. So it's stable with 6 electrons around it. So 3 pairs. Other than that, everything else obeys the rules, because if it's on the left-hand side of our blue line, it's a metal, so we can think of it as an ionic compound. Whoops, didn't mean to wipe that off. And if it's to the right of that blue line on our periodic table, or as hydrogen, these are our only 2 exceptions. Next year, I'll put these in a different colour, next year you'll encounter phosphorus, sulfur and nitrogen, which all do really funny things, so long as they're the central atom. So in the middle. This doesn't have a central, so like the magnesium here is a central atom, it's got atoms around it. Okay, so they're quite variable. Like nitrogen can have funny numbers like 7, odd numbers. Sulfur can go up to 10. So they do weird things, but you'll learn those next year. So, the octet rule is what we're aiming to do. There are some exceptions, the ionic compounds, because they are trying to empty the cation, so have an empty shell there. Hydrogen, because it's stable with only 2 electrons or 1 pair. Boron is stable with 6 electrons or 3 pairs. And there's some others you'll meet next year. But at this stage, they'll obey the octet rule. So how do we draw these things? I'm going to start with a compound CH3Cl, so it's called chloromethane. The first thing I want to look at is my definition. The definition says it's only about valence electrons, so here's where I use my periodic table, and I find where they are. Carbon is found in group 14, so I should know now, with my understanding of the periodic table, how many valence electrons it has. So it's 1, 2, 3, 4 away from the far left-hand side, so it's got 4 valence electrons. So there's 4 coming from this one. Hydrogen is in the very first group, so it's in the far left-hand side, so it has 1 valence electron. And there's 3 of them, so 3 times 1. And then chlorine is in the 7th one across in my periodic table, so it's in group 17. So it must have 7 valence electrons. This is why the periodic table is such a useful tool for us. We can very quickly predict how many valence electrons something will have. Sadly for you, it doesn't work in the transition metals, which is that block between 21 and 30 and everything below that. But in that block is an exception. You just have to know those. Alright? So we've got 4 plus 3 plus 7 equals 14 electrons. So we now know how many electrons we've got to make our Lewis diagram. And I think that is step 1 on page 123. Calculate the total number of valence electrons. Now, how to choose which one to put in the middle. The one to put in the middle is the one with the highest valency. Now, valency is a little bit different to the number of valence electrons. Valency is how many chemical bonds can it potentially make. If it's got 4 valence electrons, it can potentially make 4 more bonds to go to 8. If it's got 1, it can potentially make 1 to go down to 0 or up to 2. Okay, so it's only got a valency of 1. And 7 is so close to 8 that actually its valency is only 1. So the one with the highest valency normally goes in the middle. And in this case, this has got the highest valency. So I'm going to draw that one first. Now, I'm going to show it a little bit differently to the book, because I find this way a little bit quicker and therefore a little bit easier. There are 4 more things. 3 hydrogens and 1 chlorine. This has a valency of 4. To me, that means it's going to have 4 chemical bonds. A hydrogen, 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 and a chlorine. Now, each chemical bond is made up of how many electrons? 2. So that's 2, 4, 6, 8 already used. So, that leaves me with 6 electrons left to play with, doesn't it? Now, the other thing is I'm noticing all these hydrogens. So I can sort of tick them off. That's already got 2 around it. That's already got 2 around it. And that's already got 2 around it. Why is 2 okay for hydrogen?
Because it's a full valence.
Cool. Full valence shell there. It's one of our exceptions. Okay? It's one of our exceptions. Right. Then I look at carbon. 2, 4, 6, 8. It's good as well. But chlorine is not. So chlorine only has 2. And how many does it need according to the name of that? How many does it need in total? 8. Because it's not one of the exceptions. So it must obey the octet rule. So all I do, crosses or dots, I'm going to do crosses actually because I find them quicker in an exam. So I'm just going to go 1, 2, 3, 4, 5, 6. Whoops. So I've got no electrons left over, which means this must be correct. Let's just double check. Including the bond, 2, 4, 6, 8, we've made our structure. Gets a bit harder if we don't get ticks for everything. So I'm going to show you one where we don't get ticks for everything. Before I do, there's a hand up. Yep.
Can you use the lines as to count for the...
You certainly can. In fact, it's easier in an exam to use lines than dots or crosses.
And they count as 2.
They count as 2 electrons, so you have to remember they count as 2. Okay? So up here, this oxygen could be drawn like this. Okay, so it could be drawn like that.
So you know there's a double bond between there?
Correct. Yep. That's the right-hand way up there for oxygen is a better way to do a Lewis dot diagram. Yep.
Because on the top right one of the oxygen was a double bond, could you just draw the other two, like the other pairs of dots, as lines as well?
No, you can't draw them as lines. Good point. A line has to be between 2 atoms. It can't just be going off into space.
Okay.
For these, there's actually something I'm going to show you later where you do draw a line. Should be our toothpicks in our little activity, but they go to nothing, and that helps us work out the shape, the angles, bond angles and stuff. Okay, but for Lewis dot diagrams, no, they have to be dots.
Okay.
That's why I've chucked the word dot in the name, just to remind you there's probably going to have to be dots there. Okay, that's actually an easy one. Now I'm going to do a hard one. I'm going to do sulfur dioxide, SO2. And by the way, examiners love to give ozone as an example. Ozone and sulfur dioxide have exactly the same structure, because ozone is just oxygen dioxide, and they're both in group 6 or 16. So here's my next one, SO2. Hopefully that fits on the screen. So my first thing is to go, oh yep, they're all in group 16. So they all have 6 valence electrons, which means 1, 2, 3 things times 6 is 18. So I'm going to start with 18 valence electrons. Yes, there's more than 18 electrons in this thing. There's only 18 valence electrons, and that's all I care about. Okay, they both have the same valency. Can you guess which one might be in the middle though? Sulfur. Just because there's only one of them. Okay, so when you get a trap like this has got 2 traps in it, this question, so that's why I've chosen it. You go, oh, they're the same valency, they've both got a valency of 2. Choose one that's on its own, so sulfur. Okay, we know that those sulfurs are going to be bound to oxygen. Okay, what to do next? So I've used up how many of my electrons so far? 4. So we're down to 14 electrons now. Right, the next thing to do is to put, now this is where you should work in pencil because I'm going to end up rubbing something out. Okay, so here's where I'm going to put those electrons around the central atom first. Okay, sorry, put that wrong. Start again. I'm going to fill up the outside atoms first because they have to obey the octet rule. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how many electrons have I got left? 2. Okay. Then what I want to do is, there's only one other place those 2 can go, which is in here, isn't it? Then I'm going to check if the octet rule has been fulfilled. Is the octet rule fulfilled around this atom?
Yeah.
This atom?
Yeah.
This atom?
No.
No. Right. If you get a no, that means some of these electrons I've put around the outside, around the absolute outside, as lone pairs have to be shared. What is the sharing of electrons between 2 atoms called? Covalent bond. So they have to go into the covalent bond. This is why I'm saying use pencil. I'm going to rub those, I can choose any 2 to be honest. I'm going to rub those 2 out. And I'm going to move them into here. What sort of bond will that make now? Double bond. Good. Now let me check that the octet rule is satisfied by everything. This one hasn't changed, so yes. This one,
No.
2, 4, 6, 8, yes, because remember they're shared. This one, 2, 4, 6, 8. So this is sulfur dioxide. Yeah. No, there's 1, 2, 3, 4, 5, 6. Remember, a line is with 2. Good to ask the question though, thank you. This is one of the harder ones that you'll get. Alright, this is one of the harder ones that you get, where you have to create double bonds or sometimes even triple bonds.
Couldn't you do it with sulfur though, and then 2 double bonds go to the oxygens?
Right, I'm going to...
4 pairs.
Yes, but then we'd be left with 2 electrons that we don't know where to put them. If I put those ones into there, this sulfur now has 10 around it. Now look, sulfur can take 10 in certain compounds, not this one. Again, a good question, because you will find the sulfate ion, if you go into level 3, is really funky. I think it takes 12 electrons to be stable, which breaks all the rules that we've got. Okay, so, easy one, but we've still done the same process. Okay, number of valence electrons, ticking them off as we use them up. Harder one, same process, number of electrons, crossing them off as we use them up. Damn it, left something not obeying the octet rule, our sulfur. So we move some electrons into here to be shared, and there we go. Now what some students often say is, yeah, but now that one's sharing its own electrons, the sulfur hasn't provided any electrons to that oxygen. Just remember that all the valence electrons are involved in bonding. So this electron might end up here at some stage, might end up here or here. The electrons move around. They are all involved in the bonding and the lone pairs, so they actually do move. This electron doesn't stay here the whole time. This electron can be somewhere else, so long as it's been replaced by one of the other ones. All right. Any other questions before I stop that?